if she's talking, we should be listening, right? One question can benefit others. So yes, yeah, the conclusion is what you're implying. Yes. Answer your question. Other questions? Yes?
Can we start on exercise 15
I imagine some of you may have done it. But yes, go do exercise. Let's do it. Actually, let's look at example 24 real quick. Okay? Look at the note here. It is not necessary to show the entire truth table if it can be shown that there is at least one case where our hypothesis, as a condition of our conclusion, is false. So, then the argument has been shown to be invalid. So, if you notice on the previous example, we didn't know till the last cell, okay, the last cell was false, yes?
Yes.
If we see that one of these other cells is false, we can automatically conclude that it's not a tautology. Right then and there. We don't have to finish that last column. Okay, unless I ask you to on your quiz or your test. Right? So, it's not necessary, is what they say, to have to do the whole thing. You guys will be doing the whole thing for me. Check the validity of the following argument. If the Empire State Building is tall, then it will be struck by lightning. If the Empire State Building is not tall, it will not touch the clouds. The Empire State Building is not struck by lightning, therefore the Empire State Building is not tall. So, in this argument, okay, if you notice, okay, it's got the same form. So if you were to look at this and compare it with example 21, in example 21 we have really the same argument with different letters. You have our conditional statement implies, and then we have a not T and as a statement not C. You'll have the same format with example 21. You'll have a value as a conditional statement with another statement, and then you'll have the nots, and then a not gives you a not. So if you look at 21, okay, I'm going to leave this here. We're going to look at example 21 just real quick so you guys can see. When you look at 21, we can see that this argument's valid. It's logically valid, but it doesn't make sense. Okay, like you guys will start reading that, you're like, well, that doesn't make sense. Well, it's logically valid. If you look at, here's 21. If you look at 20, okay, this is 20, this is 25, right? Or 24. Look at how it's set up. We have a not and a not and a not and a not. Okay? Statement, statement, not, 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 not. Now, this is 21. Statement, statement, not, 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 not. This statement has the same conclusion as example 24 because they're really the same logical argument. It's going to have the same outcome. It's going to be valid. This one's valid, so will example 24 if you were to work it out. So even though the letters are different and the actual words are different, the logical argument is the same, therefore the conclusion is going to be the same and it's going to be valid. Yes?
Would that mean we can give the same reason?
Yes, because it's the same argument with different words. Okay? The logic part behind it is the exact same. Ladies, do we have a question? Where are you looking at? Let P be. The picnic is canceled. The note means that's what P is.
Oh, okay.
That's what the note means. So, again, example 21 and example 24 are the same question with different words. It's the same logical argument. So you're going to get the same results. Or you would write the same proof. So this proof right here could essentially be the same proof for example 24 because they're the same argument. Logically. Okay, so if we look at example 25, this is going to have, if we look at this one, it says, if the ocean is deep, then the log will float. The log floats, therefore the ocean is deep. So, if we look here, it is clear that the conclusion of this argument, the ocean is deep, is a true statement. That's true, right? The ocean is deep. Yes?
Yes.
Eyes up here. Okay? However, this argument is the same form as example 20. In that example, it was shown that the argument is not logically valid. The logic's argument, okay, even though this makes sense, the argument is not valid logically. Okay? That the ocean is deep, that's true. But the argument still is not valid because of our logic statements that we're going to use to prove it. If you were to try to prove this, you would show that it would be not valid. That the conclusion is not valid. This is not a valid argument. Even though it makes sense, it's not a valid argument. The example 24 didn't make sense and it was valid. Right? So last note here. Okay, the point that a conclusion of a valid argument is not necessarily true, and the conclusion of an invalid argument might possibly be true. Okay, it doesn't matter in your head whether you think it's true or know it's true or not. You're looking for validity in the argument through logic statements. Okay, through using theorems of logic. The theorems are tell us what makes it valid. Okay? So now, in exercise 16, you're going to rewrite each one in symbolic form. Then, just write each one in symbolic form and check the validity of the argument. So what are the two ways you can check validity? Yes?
The truth table and the TA table with statements and
Okay, so you either do a two-column truth or truth table. Which one are you probably going to pick?
truth table.
Truth table. Okay, ready, go. I'm going to let you guys get started on this. And then we need to move forward. How many of you guys got 10 minutes to work on it? And then we'll take some time. I'll give you the top parts of the truth table. Let me see if I've got those. If I don't have them, then you're out of luck. But I'll see if I have them. Go ahead and get started. Make a truth table. Actually, maybe I'll just help you guys start it, and then you guys can finish it. Does that work?
Yep. Start what?
You guys are going to start this, and then you'll finish it at home. So you guys go and get started, and I'll put up a answer for you when I can get one here in a second to help you out. Yeah, I'm gonna get a practice truth table up for you for exercise 16. But you guys get started, then you can check as soon as I get it up. So we're working, right? So your pencils should be going
Do we first go?
on the paper.
Do we first go F, C, and then A?
I would do this. Do FCA, yes. FCA.
And then on the second one, we do D, I, E,
DLE, yep. FCA, then DLE. I'll just give you guys the name of the columns, and then we're going to move on. We got more to do today. So. Okay, for number 1. Okay, here's your columns that you'll want to do. F, C, A. And then you're going to want an F or a C. You're going to want a C as a conditional statement with A. So if C, then A. Then you're going to want a conjunction of F or C with the conditional statement of C implies A, or C, if C then A, sorry. Then you're going to want a not A. Now remember, you got to write the symbolic form still. You got to give me a P1, a P2, a P3, and a conclusion. You need to give me that as well. Okay? The last two columns that you're going to want are going to be so what does that mean?
It means F
This guy, right? Okay, the not A goes here as a conjunction here. And then our last, we have our hypothesis as a conditional statement with F. So this is our hypothesis. And F. So these are the columns you need. Okay, I'll give you the first three here. True, true, true. True, true, false. And then you're going to want true, false, true. True, false, false. False, true, true. False, true, false. Hey, some of you need to make your F's and T's a little more clear. I'm getting this for an F and this for a T. Okay, and it's sometimes like squiggly, so I can't really tell the difference sometimes. So, yeah, write in capital letters if you can, please. Yes.
Mr. Robinson,
Huh? Say it loud again. Write smaller. Yeah, you're out to maybe just right off to the side or something. Make sure you keep track of it. Okay, FFT and FFF. Okay, so if you start off like that, it puts you on a good track. Yes?
So, when you have threes like P, Q, and R, how does this one do I think about it? So, there's one, two falses and four falses, for example, there's two falses and four falses, and then the third row is three falses, three falses, three falses.
Yeah, so this is. Okay, so the next one, you're going to want to do the same thing here for your first three statements, okay? But here's what your next one can start out like. Okay, so you're going to have a D, L, E. You're going to want a D implies L, or sorry, you can just think of L. And L, if L, then E. You're going to want D, L as a conjunction with L, E. You're going to want not E. Then you're going to want your conjunction from before as a conjunction with not E. And then we need a not D. And then you're going to take all of that. Okay? That's a conditional statement with not D. So this is your hypothesis here. You got not D here. Make a conditional statement. Okay, so this is the table you need for the second question. And you're going to fill out the truth values the same on the first three here as you did over there. Or sorry, the same over there as you did here, sorry. So make those truth values the same, that's a good way to start. Okay, get that written down because we're going to move forward in a couple more minutes here. I'll let you guys get that written down so you guys can get that done during your study holiday. Should only take you about 10 minutes once you get it all drawn. Okay? So this one should have 8 rows as well, just like that one. Make sure you give a conclusion at the end, whether it's valid or invalid for both of them, and tell me why it's valid or invalid in that conclusion. Yes?
What are we doing with what are we doing with the naughty,
The not he goes on a conjunction on the
I guess
connection.
it's,
Good question. It's hard to see if this kind of throws you off a little bit here. It's a D. Barry, assistant over here?
yeah.
I already know. I'll wait. That's fine. So valid truth tables for both questions, and you got to make a conclusion. Make sure you have the symbolic form for both questions. Okay, ask you to do the symbolic form for both. The nice thing is, I gave you the start of the truth table, which includes the premises in it, if you can spot them out. Okay? I think you guys will like this next subject we're going to do today quite a bit. I think it's kind of fun. Yeah, I think you'll like it.
That'd be good, why not?
Okay, when you're filling out a truth table, I personally like to do one column at a time. Okay, some of you like to do like the whole row. I like to do one column. That's just a personal preference. So if you're doing rows and it doesn't make sense to you, maybe try columns. If you're doing columns, maybe try doing rows. Okay, the whole purpose of this right here, this notation with the parentheses that are empty, is for you to save space. It's really all it is. It's just space saver. Okay? Just a space saver. All right, let's go to page 41. Go to page 41. The page 41 stuff? It'll be on the quiz, yes. But the quiz is until Thursday, so. So what's going to be on the quiz are valid and invalid arguments, a two-column proof, and a truth table proof, and then some of this quantifiers and quantified statements will be on the quiz too. Okay? This stuff, I really think you guys will like quantifiers and quantified statements. I think it's going to be useful. Okay, page 41, here we go. I need a reader. ideas. I'm not looking for an exact definition. We hear quantity or quantify or see how the word quantity is in here? You see that? It's like the root word, quantity, quantify. What do you think?
How many things there are?
How many things there are. Look at what this is talking about. We're talking about how many of something, right? So we're looking, there's two types of quantified statements. We have examples where all, we have examples where some or there, which in this case, the adjective all is called a universal quantifier. So that's one, universal quantifier. Next, we have the adjective some, it's called an existential quantifier. So the universal quantifier, okay, says something about every member of the group or class of things. Says something about every member. Underline this sentence right here. Underline it. Okay. The first quantifier says something about every member. Okay. And then the second one, underline this sentence, type statements that says a group with a certain characteristic has at least one member. Says a group with a certain characteristic has at least one member. Now this one says about every member. This says about at least one member. Okay? So we have universal quantifier and existential quantifier. The universal quantifier all is sometimes replaced with for all. Highlight these right here, just like this, highlight them. For all, for every, or for each. Highlight those words. That's another way to say all or have a universal quantifier. Okay? Each of the following statements says the same thing. In other words, each statement would have the same truth value. Okay? These all mean the same thing. All dogs are hounds. Okay? For all dogs X, X is a hound. Means the same thing as this. For every dog X, X is a hound. For each dog X, X is a hound. What does the X mean? What's X mean again?
Is it a variable?
It's just a variable. It's saying for every X just represents some dog, right? For all dogs, X of some group or whatever it is. Now, if we look back at this, it says something about every member of a group or class. So X represents that group or class of things that we're saying. So for every dog X, X is a hound. For each dog X, X is a hound. For all X, if X is a dog, then X is a hound. Those all mean the same thing. You need to be able to identify those. Okay? Questions? Okay. Statements 2 through 5 may seem awkward, but there are advantages to them. Okay? You use so up here, statements 2 through 5. Okay, these ones right here on the top. There's different reasons why you would use those statements. Okay? Instead of statement number 1. Okay, I need a reader for existential quantifier. Go.
The existential quantifier some is sometimes replaced with there is, there exists, or there is at least one. Each of the following statements is saying the same thing. In other words, each statement would have the same truth value.
Okay, who's reading statement 1 for existential quantifiers? Go.
What did you say?
The first statement here.
Some dogs are pointed.
Next one, number 2. With that, go.
There is a dog that is a pointer.
Next. Go.
There exists a dog that is a pointer.
Next.
There is at least one dog that is a pointer.
Next.
There is an X that is X.
Oh, sorry. Over here.
There is an X that X is a dog that X is a pointer.
Good. Will you read our note for us?
No, it is customary to not read plural in a quantifier of some, even though statement 1 about some suggests that more than one dog is a pointer. We will follow the convention of not assuming that some indicates more than one.
What does the note mean? What? Some only means one. Okay? Hey, what does this note mean? Yeah, you too. Right here in the middle. Read the note. You're not paying attention. What does the note mean? Riker, what do you got? Got an idea? Okay, what do you think, what was that note tell us?
That the stated one above seems to suggest that there's more than a value.
Okay, so the note is pointing out, and when we see the word sum, when we're looking at existential quantifiers, the word sum doesn't mean more than one. Okay? We're going to say, we're going to follow that, we're not going to assume that sum means more than one. We're going to assume that it just means one. Okay? So the next note below this, the phrase for sum should be avoided. Okay? Because it's not always clear whether or not the intended meaning is all or some. So the statement for some, right, highlighted right here, okay, for some should be avoided. For some. Okay, but because the word some, we don't want to get that word confused with more than one. Okay, we're just going to assume it means one. Yes?
Some can mean more than one, right? Like it can, like, some dogs are told that can mean one or it can mean more than one. And it's,
But we're going to follow the convention of not assuming that some indicates more than one.
but it is possible when it is more than one.
No, so we're going to follow this rule. Assume that means one. Okay? Because you don't want to get, again, we're following this idea. Because it'll keep it simple as we go forward. Okay? Does that help? Okay, terms and predicates. Consider the statements. 3 is a whole number. You guys know what a whole number is?
Yeah.
What's a whole number then? Who's got it? Who can explain? Go.
An integer.
No, an integer is different than a whole number. Not all integers are whole numbers. Yes?
Aren't they numbers without decimals?
Getting there because you're thinking integers don't have decimals, right? Okay? Okay, whole numbers. Okay, natural numbers are 1, 2, 3, 4, all the way to infinity. Whole numbers are 0, 1, 2, 3, 4, all the way to infinity. Okay? They're numbers that don't have decimals and they're positive and they include 0. Okay? So 3 is indeed a whole number. X is a whole number. So we got two statements here. Two statements. In these examples, the whole number is called a predicate. Is the whole number is called the predicate. 3 is called the term. X is also a term. You need to be able to identify terms and predicates. Okay, say, right here, I make a note, say, we've got to be able to do this. You got to be able to identify a term and a predicate. Okay? You got to be able to identify a term and a predicate. Now, let W denote is a whole number. So W means whole number, okay? When we hear that word denote, right? Denote means is, or be, let W be the predicate, is a whole number. So W represents the whole is a whole number. Thus, W3 is read as 3 is a whole number. W3 is read as 3 is a whole number. WX is read as X is a whole number. So, again, we have to know this terminology. So the first value here represents the predicate. The second value represents the term. You need to know how to read this, what this means. You need to be able to say, oh, okay, 3 is a whole number. You need to be able to say, well, X is a whole number. You need to know how to read these symbols going forward. This is going to be the hardest part about this section, is being able to understand the symbols. Yes?
What's the difference between a term and a whole number? Three is a whole number, and 3 is.
Not there yet. So 3, like the difference between the statements, they're just two statements. Is that what you're asking? We're saying, if I was to, you know in English class where you got to identify your nouns and your verbs and your adjectives? This is like that in that we're going to break up our statement. This is the term, this is the predicate. This is the term, this is the predicate. Does that make sense? To answer your question? Good. Next question.
So, is it like gonna tell you like W, but like W always means is a whole number and like.
Most of the time W will mean is a whole number in what we're doing in this class, yes. But if it changes, it'll notify you what the symbols mean. But you just have to know how to read it too. So if we keep that same notation going forward, the statement half is not a whole number is written as not, or is not a whole number, sorry, is not a whole number. Not, we know that means not, right?
So not.
So half is not a whole number. Half is not a whole number. And then we say y is not a whole number. Y is not a whole number. Okay? So yes, in this case, if W, it'll be a sign, yes. Okay? Okay, symbolic representation. So you got to begin. You got to be able to identify terms and predicates. Now we go to symbolic representation. Who hasn't read yet that wants to read? Have not read and want to read. Training read already. Gaff, can you read it?
Statements about modifiers were previously translated into symbolic form. Modified statements can also be put in symbolic form. But first, the universal quantifier for all x and the
Existential?
existential quantifier there is x must be replaced with symbols.
Okay, so when we're going to write our universal quantifier, so we want to take mathematicians, we like symbols because they save space, right? And everyone else, if I know that a symbol means, for example, if I know this symbol right here, we got upside down A with an X, that means for all X's or for every X. That is our universal quantifier. If I was to write this symbol in some other country, it's the same symbol between mathematicians. Okay? So number one, it makes us easy to communicate with other mathematicians. And who would, I'd rather write a little symbol than have to write out a whole little couple words, right? Save some space. Okay? So, that's how we write for every x as a symbol. You need to know this symbol. This symbol will not change. That means for every x, wherever you go in math world. Okay? This means there exists an x, or there exists an x, or there is an x. Sorry, there is an x or there exists an x. So backwards E with an x means there exists an x or there is an x. Yes? So this is not a term and a predicate thing. This is a symbol to help us use later. Okay, for our quantified statements, for our universal and our existential statements. Now, let's put all this together. Okay, we're going to take all this and put it together. So, we're going to consider the statement. Let T be the predicate is a tiger. So, we're assigning what T is right now. So, whose question was about W1? Okay? W meant whole number, right? So, we're assigning, well, T is going to be the predicate is a tiger. C is going to be the predicate is a cat. So now we're going to use those symbols mixed with our existential quantifier symbol and our universal quantifier symbol and make some statements here. You can use the symbols to rewrite the statement in the following ways. For all x's, if x is a tiger, then x is a cat. To rewrite that, we can say, well, if x is a tiger, right, then x is a cat. Or, if we want to replace for all x, okay, so we have is this universal or existential?
Existential.
For all, we're universal, right? So we have a universal quantifier, and then what is this? What do we know this as? An if-then. What's it called? A conditional statement. So we're using stuff we've already learned. You got a problem? Okay. So we have our universal quantifier and we have a conditional statement. Let's just replace the conditional statement with symbols. For every x, if x is a tiger, then x is a cat. Okay, so we replace this statement with this. Now, if we want to replace our universal quantifier, we can say for every x, for all x, whatever you want to, however you want to say it, for all x's, this guy, x, if x is a tiger, then x is a cat. So we took this big long statement, and we can rewrite it like this. So when you guys are writing notes in class, you could say, hey, let T be this, let C be this, and you guys can write notes to an English class, and your English teacher won't understand.
Yay!
I didn't teach you that though. No, no. Okay, but really kind of cool though, because you guys know what the symbols mean. Now, mathematicians, okay, we use this. Okay, the symbols are nice because, again, saves space. It's easy to understand once you know the language and what the symbols mean. Okay, because now you can write statements more compact, and again, they're easier to understand once you learn the language. It's like learning a new language. It's easy to understand once you learn it, right? But we've learned the language, now we're putting it together. Okay, where for every x means, for all x, the last statement is called symbolic form of the original statement. So this statement right here is symbolic form of this. What do you think you're going to have to do on the quiz? You're going to have to write in symbolic form. The quiz will have this on it. Okay, here we go. Consider a statement. Some quadrilaterals are squares. This statement is logically equivalent to the following. There exists an x such that x is a quadrilateral and x is a square. Let Q be the predicate, quadrilateral, S be the predicate, is a square. The statement can be rewritten symbolically as this. There exists an x such that, what's this mean? Who can read this for me? Let's go, let's do this. If I raise a hand, who can read this for me? Who can read this for me? What do you got?
X is a quadrilateral and x is a square.
X is a quadrilateral and x is a square. So you guys got to see this and say, hey, look, this right here, this is a conjunction. Right? Okay? We know S is square, Q is a quadrilateral. Okay. And now we want to write it in full symbolic form. We have an existential quantifier because there exists is not a universal quantifier. It's existential. So there exists an x such that is this guy. There exists an x such that. That's our existential quantifier. Such that x is a quadrilateral and x is a square. Now, this statement, can you guys think of an x value or something x that is a quadrilateral and is a square? Yes. Huh? A rectangle? So yeah, a rectangle is a quadrilateral. That's good. But a rectangle is not a square. A square is a quadrilateral, and it is a square, right? Now, let's think about this. Can you think of an object that is a quadrilateral in shape, and that same object is also a square? Yes? Swamp cooler thing. We're assuming all of those sides are equal, that vent. So yeah, that would be, depending on the Lego. The one with the little 4 dots on it. That one probably hurts worse than the little rectangle ones. When you step on it. I just stepped on a Lego the other day. It was not fun. Yes. Hey, he's talking, right? Go. A rhombus.
No, rhombus.
Yeah, your traditional rhombus is like a guess.
That's a parallelogram.
But if you turn it, it becomes wrong.
So a rhombus has equal side lengths and 2 parallel sides, yes? Or 2 sets of parallel sides. What does a rhombus, what does a square have that a rhombus doesn't? What does a square have that a rhombus doesn't? 4 right angles. So that would be the only issue with that. Yes?
Well, since a square is technically a rectangle, could we put down rectangle?
No, because a rectangle's not a square hole. We're gonna move forward. Hey, good examples. Okay. Let's look at this statement. Who wants to read? I'm tired of reading. Go, Adam.
This statement, which one?
The note. Sorry.
The two statements, all dogs are mounts, and some dogs are mounts, appear to be very.
Hey, wait till we got some people kind of doing their own thing and whispering and stuff. We'll read this statement, then we'll go to lunch. Just know.
The two statements, all dogs are mounts, and some dogs are mounts, appear to be very similar in structure. In fact, only one word of each statement is different. The difference between statements can be seen more clearly when the statements are expressed in symbolic form.
Okay. What I want you to do is go home, look at these two statements, and tell me the differences between the two.
I already know.
Okay? That's your homework tomorrow.